is not like that intuitive as like traditional machine learning. At least it was like that for me. And I encourage everyone, since we are quite a few today, that to ask questions if something is confusing or you don't understand it. It's better to just discuss it before we move on to the next slide. So this today, I wanted to, as you can see, the title is "What If Question," and it's like a special type of question, right? It's because it implies that you are asking about some alternative scenario or a hypothetical world. That's something that did not happen, and you wanna just estimate that effect, right? So it's, in that sense, it's a tricky question to answer. So first, before we dive into the algorithms or how to answer that question, I just wanted to give you an example. What is the problem with machine learning in general, and what are the use cases where if you just use traditional ML, what kind of problems you can see or encounter. That's something that I think it would be instructive to start with. So that kind of use case is a churn model. So I don't know if you done this task in your practice or not. So it's just simply you assume you are a data scientist at or some kind of organization, and you are selling a product or you are selling a service, and you have a bunch of customers, and you want to know which of your customers are going to leave your company, or churn, as they call it. So that's the idea. So you use your traditional machine learning or statistical approach, whatever you prefer, and you collect your historical data, and you just train your churn model. And once you have a model, it can obviously calculate the probability of churn, or what's the likelihood that a customer is going to leave your company, right? So once you do that, then you score your entire client base. So you compute that probability for every client that you are serving. And then in the end, you identify the segment which gets the highest probability of churn, right? Because these are the people that are most likely to leave the company. And then you pass that, I usually pass that to the customer service department or whatever department is there in the company. And then you start calling them. The people who are likely to churn, you call them because you want to retain them, and you are offering them a discount, let's say, or offering them a special service, because you want to just retain them because they are valuable to you and you want to just keep them. For the sake of simplicity, let's assume that the people that we call, or customer center calls, they are divided in two groups. Probably there are others, but just to simplify stuff, let's say there are just two groups. So as you can guess, the persuadable people are the ones who decide to stay with the company once you offer them something, right? Let's say, I don't know, some nice discount or whatever, and they decide to stay and do not churn. But there will be another segment, most likely, that will leave the company anyway, no matter what kind of offer you make them. Doesn't matter, they'll leave anyway. So then let's say it's like few months passed and you want to retrain your churn model. So to retrain your churn model, you collect a new sample, and obviously these two segments are part of that new sample, right? Because the group below is your target, and the group above did not churn, so it stayed, and therefore they are going to be part of this new sample. So and we assume that you don't change anything, right? So can you see what kind of problem are we facing if we just retrain our model on a new sample, and that sample contains these two segments? Can you guess what kind of problem is this going to cause? Yeah, it's tricky. Let's think about it. So, yeah, so let me repeat it. So the process is the following. So I built a model, the churn model. Let's say I did it for the first time. And then I applied it to my customer base, right? And I want to identify the people who have a highest chance to leave the company, right? That's natural. Then once I identify that segment, then I start calling them because I want to keep them. And I'm telling them, okay, I'll give you a discount, don't leave. Or I'll give you like a special service, don't leave. And then just to simplify stuff, I'm saying that these people with highest score are divided into two segments, right? Some of them will decide to stay because after you offer them something, and some of them leave anyway, and the lost and persuadable. So we are good so far. Now it's been like 6 months, let's say, since we trained our first churn model, and you collect your new sample. You have to retrain it, right? That's the usual practice. You usually retrain your model once in a while. And let's say, yeah, it's been 6 months, you have to retrain your model, you collect your new sample, and of course these two segments are part of that sample, right? Why not? And the question is, if I just retrain my model on a new sample, what kind of problem this can cause?
Persuaded people will be indicated as non-churners, but it is only because of me intervening.
Exactly, yeah, that's correct. So persuadable people will be labeled with zeros because they stayed, right? It's a binary classification problem. So either we have target either 0 or 1. So persuadable people are labeled with zeros because they stayed. And lost people are labeled as with ones because they left anyway. So these are our target people. Okay, so we have a new sample, and we know that among other segments, there are these two segments in that sample, and persuadable segment is labeled with zeros, lost people are labeled with ones. This is good. Why is this a problem? Can you guess?
I mean, rate of churners decreased, and I'm not able to identify who I wanted to identify.
Yeah, that's one thing, that churners, yeah, maybe increased. But
or was your question about lost?
No, I'm saying the fact that persuadable people are labeled with zeros and lost people are labeled with ones in this new sample, what kind of problem this can cause? I mean, since I'm asking, it is causing a problem, and can we guess what kind of problem this could cause?
Maybe their characteristics are similar, so
Yeah.
the performance decreases even more.
Yeah. So, and in other words, the problem is that persuadable are labeled with zeros. So what's going to happen is that new model is going to give them lower score, right? Because they are zeros. What does this mean? This means that we won't call them, even though they are persuadable. And that's something we don't want to do. We want to call people that are persuadable. But since they were labeled with zeros in a new sample, they will get low score, and therefore they won't end up in the high score segment. So we won't call them. That's one problem, I think. And the lost segment is labeled as with ones in the new sample. So they will get, again, high score, ideally, if the model is good and everything, right? So it will get a high score, the lost people. And we will call them. But that's also something we don't want to do, because we don't want to waste our resources just calling people who are going to leave anyway, right? So that's the problem, that if we simply retrain the model without taking into account the intervention that we made, it's going to lead us to wrong decisions, right? So the intervention, this is like a technical term, it's nothing fancy. It just means that you made an intervention in a data generation process, right? So when we do machine learning, we know that we observe some bunch of variables, and we know that they are generated by some unknown process and data generation process. And by using these ML algorithms, we are trying to model that data generation process, right? And everything happens naturally. But as soon as you do this intervention, like we did here, meaning that we called someone and we made an offer, that's already an intervention, because you are changing the data generation process. And that's why this can cause the kind of problem that we just discussed. Okay, so that's the message, right? There is one single thing that you remember today, let it be this one, that ignoring interventions in your model development leads to wrong decisions. So we have to, every time we make the intervention in the process, we have to account for that. Otherwise, it's gonna lead to incorrect actions. So another thing before we switch to the second part of the talk, I wanted to mention is this famous saying that causation is not equal to correlation. I'm sure all of you have heard about it, and I don't know if you've seen like the actual example why this is the case and what kind of problem this can cause. So I just want to spend a few minutes on this. So in causal, so this is like, since we talk about causation, this is obviously the subject of the so-called causal inference field. And in the causal inference literature, you have these DAGs, right? DAG stands for direct acyclic graph, and it's just the reason why people introduced these DAGs is that because it allows you to visualize the causal relationships between different variables. And two simplest graphs or DAGs that you can have is these two, fork and collider. So in case of fork, you have just three variables, z, x, y, and the structure is that z is influencing both x and y, while there is no causal relationship between x and y, right? So z is changing both. And in case of collider, it's the opposite. You have x and y, and I just gave you like specific examples here. So it could be anything, of course. It doesn't have to be these variables, right? So unemployment can affect whether you pay your loan or not, and it can also affect how much do you spend, right? It's very simple. And in case of collider, you have x and y, and they both influence z. That's the structure. That's it. The definition of two different DAGs, the simplest DAGs, I would say. Okay, so now let's start with fork, right? So what I do here, I simply generate x and I generate z randomly, and then I make sure that x and y are defined by z. That's it. So you see the histogram, and then you see there is a strong correlation between x and y, right? The scatter plot shows that there is some kind of correlation between them, and that's the so-called spurious correlation, right? It's not real, because we know in advance that x and y are not related. But we see that in other words, if I don't know about existence of z, then I observe x and y in my sample, I see that they correlate, and I might think that, okay, x is causing y or y is causing x. But we know in this simple example that that's not true. So why this is important? Because it can lead to like wrong interpretation of your model. And as you know, model interpretation is a big deal today, right? People spend a lot of time to like explain the model as much as possible. And if you have this kind of problem in your sample, then you are screwed, right? So the only scenario when you see the true picture in this specific case is if you condition x and y on z. Then the correlation, as you can see, is almost gone. So if you pick up a specific value of z and then measure x and y, whatever variable they are, then you won't see any correlation between them. So same story goes with collider, right? X and y, they are not linked, as you can see from this diagram. They are independent from each other. Therefore, if you look at the scatter plot, there is no correlation between them. R squared would be 0 in this case. But if you condition x and y on z, which means that if we measure x and y for a specific value of z, then the correlation appears, which is obviously spurious. This is, I forgot to open this. Let's see. Oh, I don't have any internet here. It's fine. 1 second. So how can I go into the full screen? One second. Okay. Okay. So this just a funny web page where the guy actually lists a bunch of correlation graphs, and I think one of them was like the number of the movies Nicolas Cage appears is correlated with 90% R squared with number of suicides in specific state of the US. So it has a big list of these stupid things, right? Just to showcase that spurious correlations are everywhere, like unless you are really careful about it. Okay, that's it. So I think it's clear up to now. Everything is clear, nothing special. And I wanted to just show you this image, it's a famous image, maybe you've seen it. So these are, as you can see, these are the levels of like thinking or whatever we can call it, or ladder of causation. So first level is called the association, and that's the machine learning, right? It's the simplest case when the job of ML is, right, finding patterns in a data and then making associations between the pattern and the target variable. So that's the simplest and first step. So second one is the intervention or the use case we just discussed on a churn example. So it's about describing the world when you actually do some kind of action, apply a treatment or an intervention to the system, and how to account for that. And the hardest part is the third one, which is called counterfactual, because it's about, imagining some alternative scenario or some hypothetical world, and you want to sort of estimate what would have happened in that world without any kind of intervention. So it's hardest because it's about the past that's already happened, and you are still trying to estimate, and you are trying to basically change the conditions in the past and then estimate what would have happened if I altered a certain condition, right? So we will talk about that a lot later, so it will become more clear. And that image is from this book. Judea, that guy is like an inventor of these DAGs or graphs that I mentioned, and he basically created a language for causal inference, and he even got a Turing Award for that. So it's a really nice book, and if you're interested in this field, I recommend it. It's not a technical book, like it's written for non-technical people as well, but it's super nice. Okay, so now let's jump to the second part, yeah, so the second part, as I said, is about, so in the first use case that we talked about, this churn model, so we said that when we do the intervention, and in that case intervention was calling the customers and offering them something, we have, and I just said that we have to take that into account if we want to do, if we want to make right decisions in our business, right? And the second part of this talk is going to be, yeah, how we should take that into account, and what would be the sort of appropriate way of measuring the impact that intervention caused or a treatment caused. So treatment and intervention, these are interchangeable terms. So they are synonyms and they mean same thing. So don't be confused about that. Now let's introduce the couple of important terms. So the first important term in this literature is counterfactual. And as I already mentioned, counterfactual is about imagining some hypothetical scenario, and when you ask yourself what would have happened had I not applied the intervention in the process. That's the counterfactual. Is it clear? All right, everyone understands this, no problem. Another important term is this treatment or intervention effect. So, and the definition is this formula, right? So TE is, T stands for treatment, E stands for effect, that's it. And the treatment effect is these two terms. So let's go through this expression in great detail, because it's important, right, to understand the notations and everything. So Y is the variable of interest that I'm trying to measure. So it could be like a volume of my sales if I run a company that sells something. So most likely Y would be volume of sales. So how much I sell on a monthly basis or on a daily basis, doesn't matter. So this T, subscript T, that Y has, stands for the treatment, right? So before we proceed, yeah, let's talk about this, what does treatment mean? And there is another term, control, in this field. So we have treatment group and you have control group. So again, let's say you are running a marketing campaign, and because you want to sell more, and you decided to run some advertisement campaign or some kind of marketing campaign. So that's an intervention, right? Because you are treating your customers with some kind of campaign. So you already are intervening into the data generation process. So therefore you have to use these causal inference techniques in order to estimate what kind of impact that marketing campaign is going to have on your sales, let's say. All right. So usually that is done using the A/B testing, right? A/B testing is like a golden approach in this field, because what it means is that you are actually running an experiment. You are not simply thinking in terms of these counterfactuals that I mentioned, but you want to run an experiment. And the way usually it is done, you identify two groups of people. So I'm saying people, but it could be anything, right? It could be your, I don't know, website. That if you want to, I don't know, change a font on your website, and you create two different versions of your website, and then you are observing which version is driving more traffic to your web page. Or in this case, yeah, to make it I think easier, it's maybe better to think about like customers, let's say, or it could be patients if we talk about the healthcare. Say instead of marketing campaign in healthcare service, it would be, let's say you designed a new drug and you want to estimate how effective is that drug, right? You want to measure the, I don't know, if it's a COVID vaccine, you want to measure the death rate. So how much the death rate is going to decrease if you vaccinate all the people on Earth or in a specific community. So, but let's say that, yeah, we are in an enterprise environment, we are selling something and we have customers. And when you launch your marketing campaign, so you want to do the A/B testing ideally, because you want to measure, yeah, what kind of impact that marketing campaign is driving, right? So in order to do that, you identify the so-called treatment group and the control group. So treatment group gets treated, or you send them the offer or through that, in the context of that marketing campaign. And the control group, there are people who are not treated. And then you start your experiment and you're observing both groups, right? And the difference, ideally there is only one difference between them. One is treated and another one is not treated. So one got the offer from the company and another group did not get anything. And then by the end of the experiment, then you measure your sales volume for both of the groups. And then at the end of the A/B testing, or at the end of the experiment, you are simply comparing these two different numbers measured in these two different groups. So that's the terminology, right? Treatment group and control group. So treatment is treated, control group is not treated. Okay, so as I said, and probably all of you know, A/B testing is like the golden approach in this business, right? And because you are actually running an experiment and you are observing, yeah, how people behave and how much sale your marketing campaign is generating. But there are like many cases when you cannot run the A/B testing because it's not ethical. For example, if we, let's say, imagine ourselves in healthcare, in some cases it's not ethical to do some tests on people for testing your new drug or something, or it could be too expensive, or it takes too much time to run the experiment and you don't have that much time. I mean, there are, I think, many cases when you cannot afford to do the A/B testing. And today what I'm going to talk about is for that case when A/B testing and experimentation is not possible. That's also important to remember. Okay, so let's get back to this equation, right? So first term, so y again is the variable of interest that I'm measuring. It could be again sales, for example. T, capital T stands for the treatment group, which means that I'm measuring variable y for the treatment group and not for the control. So small t is just a time, and for the sake of simplicity, imagine it's binary. So if small t is 1, this means that intervention was already done, or in other words, it denotes a post-intervention period. And when small t is 0, it indicates pre-intervention period, or a period when intervention is not done yet. So W is also binary, and it again indicates whether treatment or intervention was done or not. So if it's 1, then we know that intervention is done already, and if it's 0, there is no intervention. Okay, so first term then means that is the value of my variable in a treatment group after the intervention. That's the first term, right? So and it's perfectly observable quantity. I can observe it. So now the second term, as you can see, it's a counterfactual. So why is it a counterfactual? Because you see that y has a subscript t in a second term, and as I said, t means treatment group, or a group that was treated. But at the same time, w is 0, and as I said, when w is 0, there is no treatment. So having subscript t and w being 0, they contradict with each other. So, right, how it can be that I'm saying that this is a group that was treated, but at the same time I set w to be 0, which means it's not treated. So that's why this is counterfactual. Or in other words, this is a quantity that cannot be realized in actual real life. So what it means, the second term basically means that what would have been the value of y in a treatment group if I had not applied the intervention, right? That's the counterfactual. Is it clear? Okay. So that's all. So this is a very natural definition of treatment effect, right? Because the first term tells me what is the value after the intervention, and second term is what would have been the value in the exactly same group without an intervention. That's the effect. That's what I want to measure. If I want to understand how much gain did I get in sales after I launched the marketing campaign, then I should know what kind of sales I would have without that marketing campaign. And that's not observable, right? Because we can't go back in time, and we can't change the condition and observe the potential outcome. We can't do that. By the way, did you see this TV show, Dark Matter? Do you know, guys, TV show Dark Matter? So there is this, he knows, this crazy physicist who actually designed a box, the big box, and if you go into that box, it allows you to visit different, alternative worlds of yourself. And it's based on this fancy quantum mechanical notion. It's called superposition. In the beginning of the 20th century, physicists concluded that if we talk about elementary particles like electrons, they can be in a superposition, meaning that the particle can be in two different states at the same time. And in this TV show, this mad scientist managed to apply that law to macro or human beings. And if you are in that box, you are in a superposition. So you can be in any world, basically. But so we don't have that box, so and we can't go back in time. So we can't observe the actual counterfactual, right? Because that's not observable. And I think it's clear. If this is not clear, let's talk about it, right? Because this is important. Then it doesn't make sense to proceed. Okay, so commonly, if you read books or papers on this topic, usually people are interested in this CATE, or conditional average treatment effect, right? So usually you want to average, you are looking for an average treatment. right? If you have like a sample and you want to measure the impact of your marketing campaign, let's say, on average. And another important thing is that you want this term conditional. And that conditional is, as you can see, on the last expression, we take the expectation value of treatment effect conditioned on X, right? So why is that? So if I run again this marketing campaign, then I might need to know how much effect it generates, let's say, for younger customer base versus older customers. Let's say X, if X is an age, or it could be, I don't know, demography, like location. I want to know, for example, the effect of this marketing campaign in Batumi versus Tbilisi, for example, right? So the conditional treatment effect, yeah, is more granular than just treatment effect, right? Average treatment effect, and that's why people are usually interested in this quantity rather than just treatment effect. Okay. Yeah, then there is this uplift. So as it says there, uplift is same as treatment effect. So treatment effect is rather scientific term, but the business term for that is uplift, right? Because you might have seen or read this term in the blog post or something, because it's a more common than treatment effect. So I just want you to know that uplift is just the same as treatment effect, and usually, when someone might say, what is the uplift in sales, for example, which means that, what kind of gain I got in sales after I launched this marketing campaign, let's say. That's all. Okay, now, now the question is, I want to estimate this kate, or average treatment effect, and as you saw, we have two terms. First term is perfectly observable. We know everything about that because we know the people that were treated, and we observe them, and we can measure how much sales I generated after the intervention. So that's no problem there. So problem is with the second term, which is counterfactual, and it's not observed because, again, it means that it asks what would have happened had I not applied the intervention, which we don't know. And obviously, it's not observable, and one has to make approximations, right? There is no other way. You have to make approximation in order to estimate that second term. And the rest of the slides are basically about the techniques, how you have to approximate that properly. This is the first approximation. So what is it? So I'm saying that let's replace the second term with this one. What's this one? This one is the value of y before the intervention, right? So I'm saying that the value that potentially could be realized without an intervention, or the value of the counterfactual term, is the value that I observed before the intervention. Do you like that approximation? What is the problem with this?
Yeah, my question would be, are there some theoretical guarantees or conditions under which you can efficiently replace one with another?
You mean this approximation, this term with, no, it's a bad approximation. And I'm just, do you think why it is a bad approximation? What is the problem? You can make that approximation, of course, no problem. But why is it a not so good approximation? So remember, I'm saying, if I do that approximation, I'm saying that the value that would have been realized without an intervention is the same, actually is equal to the value that I observed before the intervention. Yes. Yeah, exactly. Yeah, it's a like approximation across time axis, across time dimension. So this is a bad approximation because the variable y is evolving anyway without even the intervention, right? Y is like a time series, right? It might have a trend, it might have a seasonality, so it is evolving in time. And if I make this not so good approximation, I'm saying that the only reason why yt changed is due to intervention. That's what I'm assuming. But that's not true, because even without intervention, or even without my marketing campaign, my sales is going to change anyway. And that's why this is a bad approximation, because I'm saying that, okay, whatever change I see before and after intervention is due to the intervention. But that's not true, because y is changing anyway. Is this clear? Okay. Okay, there is another approximation, and this is also a bad one, because I'm saying that, okay, I have a control group, right? I can find people who were not treated. This is control group, as we described earlier. And I can replace the counterfactual with the control group, the value of same variable in the control group after the intervention, right? But this is also the bad one, because, or it's not a bad, but it's a crude approximation, because it assumes that control group and treatment group are very similar with each other, right? I'm assuming that treatment and control, these two different groups of people, they are behaving like in the same way before the intervention, and they would behave exactly in the same way after the intervention. That's the assumption, if I'm going to use that expression, that approximation. But remember, so if we are not in the mode of A/B testing, it's not under my control who is the control group, right? Because if I can do the A/B testing, then it's under my control who I'm going to treat and who I'm not going to treat. It's me that I'm deciding who to treat or not to treat. So treatment and control groups are under my control, and then that approximation makes sense in that case. But we are not considering that. We are in a mode when A/B testing is not possible, or for whatever reason. There are multiple reasons, right? And therefore, choosing the control group is not under my control. So I'm not guaranteed at all that control group is going to behave in the same way as the treatment group after the intervention, at least. So that's also bad. And what people usually do is, so as Shota mentioned, the first one is an approximation across time dimension, and the last one is across the space, in that sense that time is the same, t is equal to 1 in both terms, but I change the groups. First is treatment, second is control, and let's call it that this is an approximation in a space dimension and not time. So what people usually do is that they combine these two approximations into a single one. And that one is called a DID estimator, and which stands for difference in differences. And in short, it's DID. So let's explain this in detail. So the one in the box is, again, our counterfactual term. That's not observable. And DID approximation says that let's approximate this counterfactual with these two terms. So the first term, let's talk about the first term. So can you read what is the first term? Like based on these notations, what it means, the first term. So the value of y in treatment group before the intervention, right? So because small t is 0, means this is a pre-intervention period, therefore w is 0, no treatment was applied, and capital T means treatment group. So the first term is the value of my variable in a treatment group before the intervention. Clear, right? So now let's explain the second term, and then we combine, and it will become clear. So what is the second term? So it's a difference, right? And both terms are from the control, or a group that was not treated. Therefore, both terms are observable. That's important to note. So more precisely, in the above formula, there are three terms. All of them are observable, as it should be, because if they are not, then this is not an approximation, or it's not any useful approximation. So let's look at the second term in parentheses. So there is a difference. So what is it? So it tells me what kind of change I observe in a control group after the intervention, right? Because it's a difference of the same variable before and after intervention. T is 0 in the last term, and T is 1 in the second term. So the expression with the bracket, which called this control group trend, it simply tells me the change that I observed in my variable for the control group. That's it. So now you see that I'm adding up the first term and the second term. First term and the one in the parentheses. So why? Because I'm saying that whatever change I observed in the control group, then same change would have happened in a treatment group without intervention. Right? That's very simple, I think. This assumes something. This assumes that control group and treatment group are similar. Again, that's an assumption, right? So just to repeat, the second term tells me what kind of change I can observe in a control group without a treatment, and then I assume that same change would have been occurred for the treatment group as well without an intervention. Therefore, I add these two terms to approximate the counterfactual. So once we plug that definition or an approximation into the formula of Kate and rearrange the terms, we get this kind of expression. So that's why this is called difference in differences, because there are just differences in the formula. So again, let's look at the first parenthesis on the first line of Kate. So what is it? It is a change that I see in the treatment group after the intervention, right? Yeah. Yeah. Intervention could be different things. In this, let's say, marketing campaign, or let's say the one that we called, or you call your customers and you are offering them something, right? You do something, you make an action, and that's an intervention. It could be anything. Or in a healthcare industry, you have a new drug or a vaccine, let's say, and you vaccinate a certain number of people. That's an intervention. So you make some action. That it could be anything, right? Or in business industry, the most common thing is, you are running an ad campaign, and then you want to measure to what extent your sales increased because of that campaign.
Okay, for example, in healthcare example, the treatment is a separate thing and the vaccination is intervention.
The same. It's the same. Treatment and intervention is the same thing. They mean the same thing.
Struggle with T and W,
So W, that's why, yeah, it's tricky. That's why I said in the beginning it's tricky. So T and W ideally mean same thing. They are the same because T means treatment, W also means treatment. But the reason why I need W is to define the counterfactual. So if you look at the term in the red box above, right? Because you need W as well in order to mathematically just write down the definition of the counterfactual. So, because if you look at the red box above, so it has subscript T, right? Meaning treatment. And when I'm saying treatment, I mean intervention. I mean I did some kind of treatment to that people. But at the same time, W is 0, which contradicts the treatment group. Because W0 means there was no treatment. So that's why it's a little tricky. Because that term means some hypothetical case.
You mentioned that we have treatments that are all observable, which were three observable, or you said not observable.
So all three of them on the right-hand side are observable because nothing contradicts with each other. Yeah, first term is just a treatment group before the intervention, right? So second term is control group. These are the people that are not treated at all. And I can perfectly observe them before the intervention. I mean, when I say before or after intervention, does not necessarily mean that intervention was applied to that specific group. So for control group, does not matter when intervention was happened. It's just for us to do the measurement. Yeah. After the intervention. Yeah, control group, when I say control group, W is always 0 because they were not treated, right? Makes sense. But small t in one term is 1, in another term is 0, just meaning simply that measurement of the control group before and after intervention. That's all. Okay, so yeah, let's look again, this Kate formula. So let's look at the first line. The first line, both terms are observable again, right? I can measure them. There is no counterfactual there. It just simply tells me what kind of change I can see in the treatment group after the intervention. Yes, right? It's no problem. I think there is no problem because I can measure the value of sales before I start the campaign. I can measure it after I start the campaign, and I subtract them, and whatever I get, that's the first term, right? So before the intervention it was 100 million, after intervention is 200 million, so difference is 100. That's the first term. But if we just look at the first term, that's not our treatment effect, right? If I simply take the difference before and after intervention for the treatment group, I get some, let's say, positive number, $100 million or whatever. So it won't be, this change is not just due to the intervention, right? Because, as I said, sales is a time series. It is evolving in time naturally. So it would change even without the intervention, right? So because I might have a trend in a time series, so it's an increasing trend anyway. So it would go up even without my marketing campaign, right? Very, very simple. So if I just take the first term as an approximation, it's going to be wrong because first term is just the difference between sales before and after intervention. But that's not the effect that marketing campaign caused, because besides marketing campaign, my sales have trend or seasonality, and it would grow up or go down anyway without launching a campaign. So, long story short, the first term or a change that I observe after the intervention is due to multiple factors: the intervention, trend, and seasonality. Let's forget others. Just for simplicity, let's say that I have these three factors that is causing a change in a treatment group, right? Intervention, trend, and seasonality, let's say. So my goal is to cancel out the effect that comes from trend and seasonality, because I'm interested only in the intervention, to measure the impact of the marketing campaign, and that's it. But as I said, first term, or the change that I see in the sales is not just, there are multiple factors that are driving the sales up. Therefore, I have to cancel out the other factors. And the second term, the last line, is doing that. So why? So second term is the same as the first line, but just for the control group. And we know that control group is not treated. There was no intervention in there. Therefore, the change that I see in sales for the control group is not due to the intervention, but some other reasons like trend or seasonality, or both of them. Right? So the intervention effect is not in the second term. There are all other effects, but not the intervention. So therefore, I subtract the first line and second line just to cancel out all other effects from the first term, so that I'm just left with the intervention effect. That's the idea of this approximation. And of course, as I said, it assumes that control and treatment groups or time series are similar. Okay, but that's a strong requirement. So this is another way of writing this approximation. I don't know, it's not a big deal. I just wanted to write it down. Instead of taking the difference in the first formula for the counterfactual, I'm taking the ratio, and because it just gives a more general approximation. So if you look at the last line, it's the same formula as on the previous slide. Only difference is this prefactor in front of the second term, right? This ratio, as you can see. So and it reduces to the first one if that ratio is 1. So let's skip this one. It's not important. So the idea estimator, requires to have similar time series in control and treatment groups. And let's say, it's, as I said, choosing a control group is not up to me because it's not A/B testing. So what if I don't have a similar, I cannot find like similar time series to the treatment group, right? And then this is another approach is used. It's called synthetic control. This is a very simple idea, I must say, but very powerful. It's really clever. So what it does, right? As the name suggests, so it allows you to create artificially your control group, because you could not find the one such a control group that resembles very much to your treatment group. Therefore, this is another option. You have to artificially create your control group. And how this is done? So let's look at this graph. So the black line, a solid black line, is Y, our variable of interest, or sales, let's say, to be more specific. And then look at the red and green lines, X1 and X2. So X1 and X2 in this example are some additional time series that I could find and I can access. And I have two requirements for those X1 and X2, and it will be clear why. So first of all, the intervention that I'm investigating should not be impacting X1 and X2 variables. At least explicitly, it should not be affecting them. And the second requirement that I have for X1 and X2 is that they can explain my variable of interest, or in this case, y. So, which means that if I train a machine learning model on x1 and x2, and y being a target, then I can accurately predict y. That's what I mean, that they should explain variable y. So if I can find, in this example there are two time series, x1 and x2. So if I can identify any number of time series. So if I identify time series that are not affected by the intervention and have a predictive power for y, then I can do the following. I will train the model where x1, x2, and x10, whatever, are the input to that model, and y is the output of that model, let's say. So, and that model is basically my control group. So why? Why is that? So look at this graph. So black line is y, as you can see over there. Model predictions that model is making is this solid blue line, and as you can see, solid. I don't know if it's visible on the screen, but the solid blue line and solid black line really sit on top of each other. So this means that I built a really accurate model. I can predict y with really high accuracy using x1 and x2. And this vertical dashed line is intervention, or a time when intervention happened. Okay, so then if I have a model that can accurately predict y before the intervention using x1 and x2, and x1 and x2 were not affected by the intervention, then I assume that the model predictions after the intervention serve as a control group, right? And this dashed blue line is the prediction of the model after the intervention. So I can make these predictions because I know the value of x1 and x2 for the whole time horizon. So I can plug into the trained model, and I can compute the value or a prediction for y, and that can serve as the control group. Those predictions are the values that I can observe in the control group. So the treatment effect then would be just the difference between these two lines, the black line and the dashed blue line. So it's a very simple, I think, approach, but very powerful, in my opinion. Because, yeah, I mean, it's not easy, I guess, to find this time series like x1 and x2 that can accurately predict y, but at least you don't have that requirement that you need to have a control group that really resembles your treatment group. So that, which is a very strong requirement. Okay. So there are like another approaches. So this one, for example, so you train a single model on a treated group, you train another model on a control group, right? You have two different models, and therefore the prediction of that model on the left would be the value of treatment group, and prediction of the model on the right would be the value of the control group, and taking the difference between them would be your kate. That's one option. You can combine that in a single model approach by combining treatment and control samples and adding this W as one of your features. W, as you can remember, indicates whether someone was treated or not. And then I'm happy, right? Then I train a model, and I can again compute the kate by plugging in W1 in a first term and W0 in a second term, and the values of X, and do the kate and compute the kate, so no problem. But the problem with this approach is that you have to train, let's say, two models in the first case, and the model have their own errors. The predictions have errors, and then when you subtract them to compute the kate, yeah, you don't know what's going to happen with that error. We are not guaranteed that these errors will cancel out each other. Most likely the error will increase. So people started thinking about how to model this kate explicitly, right? Without building models for y. And let's talk about that. And then this is like a last approach. Yeah. Mm-hmm.
How do you understand in two-model approach? Is it anomaly or it's intervention of our marketing? I don't know.
Yeah. I mean, so it's based on the historical data, right? So you launched your campaign at some point in time in the past. So you know the people that you treated, right? You have that sample. And then you collect these X variables for your customers, let's say. And you know that all of them were treated, right? And then you observe your outcome variable. So yeah, it could be, as you said, yeah, it could be an anomaly or something like that, and you can have an observation that's not due to intervention necessarily, right? Something can happen. Yeah, that's possible. I don't know. I think, yeah, further domain knowledge or expertise, subject expertise is required, and you need to just know, understand and validate your data before you train your models, that whatever values I see in Y, actually they make sense and it's not just like some kind of anomaly or whatever. It's possible, you are correct, that you could have something like that, but I think that you need to do like some pre-processing before you train your models, just to make sure that whatever values you see for your target variable actually make sense and it's not like strangely high, let's say, or something like that.
Can I ask a question? What time horizon do you choose for this, for example, approach? How do you decide?
Yeah, that's a good question. Yeah, that's like a. We will talk. I think in one of the sessions in the future, I'm going to talk about that. It's a A/B testing kind of question, because when you design your, let's say you want to start your experiment, you know what kind of intervention you want to do, and you chose already your treatment and control groups. How you choose those groups, that's totally different question, and it's tricky as well, because you want your groups to be really ideally, in an ideal scenario, they really need to be very similar and same, and only difference that we have should be just an intervention between them. But that's in the real world, that's not going to happen. So there are many factors that people usually consider when they start the experimentation. So first is how you design your treatment and control group so that they are really similar. Second is your question, how much time you want to observe that experiment, and when you have to stop and say that, okay, now it's time to stop, and whatever change I can see between these two is the statistically significant change. And another factor is the sample size. How big should be your treatment and control groups in order to get statistically significant results, or uplift in this case. I think we will talk about that at some point. But in this case, as I said, it's not an A/B testing scenario. So it totally depends on, I don't know, use case or how people actually made those experiments, or if it's wasn't an experiment and it's just simply launched a campaign. Yeah, it's I think more like a business kind of question rather than statistical question, in my opinion, because when I'm not an expert, by the way, in A/B testing, but when I hear them when they discuss, a lot of domain knowledge goes into the decisions for how long they want to run it. Of course, there are some statistical methods to calculate how big should be the sample, and maybe, probably how long the experiment should be running. But yeah, there are like interaction of many things, I would say, not just statistical reasoning, but also the business. Usually the business insight goes into this. But yeah, it's a valid question, of course. Yeah, but I don't know how we can control that in this scenario, because here, yeah, you are not running an A/B testing. It's not under your control, basically. How long you observed your experiment. You just launched a campaign, let's say, and then, yeah, you have to introduce some kind of cutoff in your time horizon and say that, okay, the impact of my campaign, yeah, it lasted up to this point and that's it, right? There is this, I don't know if you've heard about market mix modeling. There is a technique that allows you to, let's say when you run the campaign, so you do it through multiple channels. It could be TV, radio, I don't know, advertisement on the street, right? Usually it could be social network. And this marketing mix modeling allows you to break down your sales across these channels. And because you want to know which channel is most profitable. Is it TikTok, is it Facebook or something? And when you do that, they call it ad stock transformation, and ad stock transformation allows you to measure for how long your effect of this campaign lasted in time. That's one way of measuring it. It's like I forgot the name of the distribution, but it has this kind of shape, like a Poisson kind of shape. So it goes up in the beginning and then it saturates and goes down, of course, as time goes by. So one way of estimating how that effect of campaign is distributed through the time is this ad stock transformation, which is a part of this market mix modeling. Okay, shall we proceed? Okay, so one last method and then we are done. So as I said, the motivation of this slide is that we want to model this treatment effect explicitly, not just compute the first term in a Kate formula and second term and then just subtract them. No, we want to just compute or model that difference explicitly. So let's do this for the binary target case and then we will generalize it. So if we do the binary classification, then the definition of Kate is this formula. I think makes sense, right? Probability of success for the treatment group and the same probability for the control group. And the difference between them would be treatment effect. So to do to model that difference explicitly, or Kate, they introduced this transformation Z. So Y times W, both of them are binary, and we have these 4 different scenarios for Z, right? So Y, W are both binary, therefore we have only 4 scenarios. No problem. So let's compute the probability of Z being 1. And when Z is 1, we have 2 cases only. So when W and Y are both 1, or W and Y are both 0. That's when Z is equal to 1. Therefore, that probability of Z being 1 given X is the sum of these 2 terms. It's just a simple formula which takes into account this formula for the joint probability. So it's nothing special here. So then people usually make this approximation that probability of being treated and not being treated are equal, and it's 50%. And that's called assumption of balanced treatment, which obviously cannot hold in real life, and we will talk about that shortly. But anyway, to simplify stuff, let's assume that probability of W being 1 is 50%. So therefore, I can rearrange the terms, and I see that if you look at the last line over here, so this difference is a Kate, as you saw on the first slide. The difference between these 2 is treatment effect, which is simply defined by P of Z being 1. So long story short, if I make this transformation, this one, Z equals y times w plus 1 minus y times 1 minus w, very simple transformation, and I train a model for z, then the prediction of that model is simply proportional to treatment effect, right? So output of the model multiplied by 2 minus 1 is a treatment effect. So that's how you can model your treatment effect explicitly by doing the transformation. So let's do a more general case. We do transformation, this one, like, which looks more complicated, and small p over there is called the propensity score, which is probability of being treated. That's it. That's nothing special. And if we use that transformation and compute the expectation value of z given x, we get this, and we plug in that definition of z over here in that expectation operator, we are left with this expression. And then the same expression, I didn't change anything here. But then we have to make this assumption. And this is a really very reasonable assumption. It simply says that whether I treat someone or not doesn't have to do anything with the outcome, right? Because if I treat someone based on what I expect the outcome to be, then the whole thing, it doesn't make any sense, right? Because you want to treat someone without knowing what kind of outcome value you expect from them, right? So in other words, just to translate it into the marketing campaign, so you don't want to, when you are running your marketing campaign, you are not choosing the people based on who has a higher chance to buy something or not, right? Because if you do that, then you get a very biased estimation of your treatment effect or uplift. So that assumption has to be made, and that's the very reasonable assumption. It really needs to hold in order to make sense, all of this to make sense. And then this assumption simplifies stuff. You can sort of break your expectation of your product as a product of expectations because they are independent, and then terms cancel it out, and you are simply left with kate. So with that transformation, you can basically, and just training your model as a z being your target variable, you can explicitly estimate your treatment effect. Okay, and this is my last slide. So I went through like 4 different approaches, and I think it makes sense to club them into these 2 different buckets. So these first 2, I call it estimation. Why? Because you use these 2 when intervention already occurred, you already observed the value of y or the sales, and you just want to measure what kind of impact the intervention made. In that case, you can use these 2. But the other 2, like the last one, the 2-model approach or the target transformation that we just talked about, they are designed to predict your treatment effect. So they are designed to estimate your uplift even before you make the intervention, right? That's the difference. At least that's how I see them. It's not like that's how I see these 2 different approaches, right? So the first group is used when treatment already occurred, and the second group is used when it did not occur, and you want to predict what kind of uplift you are expecting. And just a special note for the synthetic control, I already said about it, it's really powerful because you don't have to find a control group that is really similar to your treatment group. You can achieve your goal even without such a control group. You can. So I won't repeat it again. So it's on the slide. Yeah, that's all. So if in case you guys have questions, we can discuss them. If not, yeah, thank you everyone for coming. Thanks. So I know, I mean, maybe it was too tiresome. I don't know. It could be because there were a lot of technical stuff, but I don't know. I tried my best to explain in detail. So, yeah. If there are something, then we can discuss, or yeah, we can even discuss it on I don't know, on LinkedIn or something. We can chat over there as well if you have come up some questions later. I don't know. Okay. So about the next one, we are not sure yet because Shota is away, I'm away also for the next few weeks, and I don't know, maybe in the beginning of July we will plan something again and we will announce it. Yeah, we wanted to do this session much earlier, like by the end of the May. That was the plan, but then, yeah, because of the situation in the country and everything, yeah, I think, yeah, it wasn't a really good idea to get together. And but yeah, let's see. We will let you know what will be the next topic and when we will do it. Most likely in July, but I don't know. Maybe July is not really a good idea because a lot of people are away. Yes, Katie. Yeah, that was the goal. But yeah, we couldn't do it this time because the first one was by the end of the April. This is the second one, and I don't know. Maybe I said July, but I don't know. Maybe July is like people are away and everything. Maybe I don't know if it's a good idea to have it in July as well.
Might be, but so at least in July we will have two, right? One from me, one from you, and one from
Yeah.
my friends that I have quite close negotiations. And if you have like willing to discuss some technical topics that you have some experience, have some expertise, please.
Yeah, I think when Shota and I just started discussing about these meetings, of course, it can't be that just two of us are always talking, right? It's not maintainable. So we expect, if you have, I mean, if you're just willing to share your experience, your problem, feel free to reach out to us. I mean, it's always interesting to listen to what other people do, right? What kind of problems they are facing at work or in a personal project. It doesn't have to be work necessarily. So, yeah.
All the requirements should be technical and related to usage of data of some kind.
Yeah, exactly. Yeah. Okay. Thank you again. Yeah, thanks, guys. Hey.
Sorry, yes. Can I ask you a question? Maybe I misunderstand first question about churn.
Yeah.
Maybe I misunderstand. Could you please repeat
What is the problem?
Yeah.
Okay. No, don't be. No, it's perfectly.
I'm shy about I misunderstand this question and I didn't.
Yeah, it's tricky. Don't worry. So, let's go to the slides. Maybe it will be easier for both of us. Okay. So what I meant is that, let's say you built your first model for the churn prediction, right? And then usually what you do is you identify the people who got like higher chance of leaving your company, right? And then what usually happens is that the marketing team or someone, I don't know, in the company contacts them, right? And they are offering them something. That please don't leave, we will give you a discount, for example, or we will give you some extra service, whatever. right? And once we do that, then just to make it simple, some people, these ones, they will stay because they will like for them, but some will leave anyway. They decided to leave and they don't want to stay, so they left. They leave anyway, no matter what we offer them, right?
Yeah.
Okay. So that's everything's good so far. Yeah. Now, let's say I want to retrain the model. It's been 6 months since I trained it for the first time.
It's new data, right?
Yeah, so I get a new sample. Historical sample, obviously, because I need to observe my customers and I need to know their behavior, and then eventually I calculate the target. I want to know whether they left or stayed with us.
Yeah.
Okay, in that new sample, we have these two people or these two segments as well, right?
Yeah.
Do you agree or
Yeah.
not?
Yeah.
You
I
agree?
Yeah.
Yes. We have these two segments as well in there.
So we have regression task about how many people live, right? Or
Not
classification.
how many. Yeah, it's a classification.
Classification.
We just, we are asking what's the probability that you leave the company.
Okay.
That's it. So, and we built that model. We identified the people with the higher probability of leaving. So we contacted them, and some of them decided to stay. Let's call them persuadable. Some of them decided to leave anyway, no matter what we offer them. Okay? Now we have to retrain the model or build completely new model, doesn't matter. So we have a new sample, we collect a new sample, and that new sample contains these two segments as well. These people are part of that new sample, right?
Yeah.
Because these are still my clients, so I include them in my new sample. Okay, and they are labeled with zeros because they stayed. But I need these people as well because they left, so I need ones in my sample. Therefore, I have to include them as well in my new sample, right? Okay, if I do this, and then I train the model on this new sample, what will happen? These are labeled with zeros.
Yeah.
So they will get low score, low probability.
Okay.
Because I labeled them as zeros, right? And ideally, the model should assign them low probability. Do you agree or not? I mean, I'm not saying that the probability is like zero, but it could be 40% or 50%. I'm saying it's not high.
Okay. Yeah.
Right? Because they are labeled as zeros. So model is trying to assign low probabilities to zeros and high probabilities to ones, right?
Right.
Yeah.
But what metrics we use? So some like accuracy, or it doesn't matter?
Doesn't matter.
Okay.
Or it matters.
It matters.
Yeah. But I'm saying if I do this naively, like I usually do. Like I don't.
Accuracy or something.
Yeah, accuracy or rock score or precision or recall, whatever. Okay.
I don't get why low score if we have some recall precision. I understand the problem will appear if we will use accuracy, but if we have recall precision, it's just too.
Let's don't think about metrics.
Okay.
Don't think about metrics. Let's think about I trained a model, new model, and I compute this probability for every customer in my sample, right? So these people.
Yeah, I get it. So it will be loss. Yes. It will be loss because zero.
Yes.
Yeah, category. Okay, I get it.
Yeah.
I'm sorry. I just.
No
I'm
problem.
thinking about metrics and maybe I just.
No. It's just a probability.
Yeah. Thank you very much, Andro.
No
Thank
problem.
you very much.
No problem. No problem
It
at
was
all.
brilliant as usual. Thank you very much. Thank you.
Thanks a lot. Thanks for coming.
Thank you. Have a nice day.
Same to you. Okay. Როგორ ახარ? გაუშვიდა?
და გავუშვიდა.
არა ვიშევს. არა. მე შეგვიძლია გავილაპარაკოთ ცალკე. ხო. კი. 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 კი, ორია, კი. მართალია. კი. კი. ჯობია ესა. გამარტივება. აბა რომელზე? გამოგწო, მოდი აქეთ დადექი. ბოლოში რო იყო?
არა, დადექით.
აბა საით წავიდა მითხარი.
გავიჭყოდი.
სწორად მივდივარ?
მე მგონი კი. ხო, აი, ზევით.
აბა. აქეთ, მაღლა?
აი ეს მე მგონი. ხო, აი ეს ფორმულა რო
აი ეს?
ხო, საბოლოოდ მისაღები ვარიანტი რომელიც იყო ეს იყო, ხო?
ხო.
შევთანხმდით
კი, ერთ-ერთი სხვათ გონივრული მიახლოება.
მაგალითად кейსი რო აღვეღო, რომელზეც ვიტყოდით, რომ აი მაგალითად
კი.
ინტერვენცია შეიძლება იყოს ეს,
კი.
მაგალითად ეს.
კი, მივხვდი რასაც ამბობ, მე მგონი მივხვდი, კი. მართალი ხარ, ხო, შეიძლება და კონკრეტული მაგალითი მოგვეყარა, ხო, მაგას მეუბნება. კი. კი, კი.
ეგ გავარჩევ. ერთი მაგალითი, რომელზეც მე მიხვდები, რომ იმიტომ რომ რაციონალურად მოყვები. მაგრამ გაგების დონეზე გავიგე, მაგრამ იმდენად ის არის ახალი ტერმინებია ჩემთვის, რომ აი სიღრმისეულად ვერ ეხარ შენ მიყვებოდი, მოყვებოდი, მაგრამ რაცა ის ჩემით რომ მკითხვა ხა ვერ გადმოგცემ რა მომისმინე რა
მე
წიგშიც უკვე ესეთ დონეზეა.
არა ვიშვის, ანუ მე დასაწყისში ვთქვი, აი, არიყავი და იმიტომ, რომ არის ისა მეთქი რა, რთული საკითხი და უბრალოდ რთული კი არ არის, აი, არაინტუიტიურია რა და თავიდან მეც მიჭირდა. ხო, ანუ უნდა ცოტა დროს აი რაღაც დაუთმო რა, წაიკითხო და მე მაგრამ პირველად რო იწყებ, ხო, ყველას უჭირს. მეც მიჭირდა რა,
აი ბობომ გაიგო.
ძალიან კარგი განხარდა თუ გაიგო.
მას სახეს ამუშავ გამოცდილებაც აქვს.
კი, მაგასაც დიდი მნიშვნელობა აქვს. რომ ფიქრობ მაგ საკითხზე მე ადვილად იქნება. ისე არა რა, ტრიკი არის ცოტა, თითქოს ადვილია, მაგრამ თლად ადვილიც არა და დაფიქრება უჭირდება და ერთ შეხვედრაზე ძნელია.
კი, ამის გარდა მე მგონია ეს პრობლემები რაღაც დროის მერე კიდე გადაიხედება და დაიხვეწება ეს ხო არ არის რაღაცა ეს ანუ ზუსტი მეცნიერება რომელიც
არა, ხო, იქნება კიდე სხვა მიახლოებები, სხვა ალგორითმები და რა თქმა უნდა, ცოცხალი პროცესია.
ეხლა ეს რაღაცები ალბათ Python-ში გაპირობებულ რაღაცებად დაწერეს.
რა თქმა უნდა, რა თქმა უნდა. აი აქ რო ვახსენე. ხო.